Hello folks, today we are going to solve 3 problems in Archimedes Principle. I hope you have a notebook and pen ready. As and when you see a problem, pause the video, try to solve the problem on your own and then check my solution. Right? Here is the first problem. Now before I start doing this problem, note something important. If the density of the object is less than the density of the liquid, it will float, partially submerged. If the density of the object is more than the density of the liquid, it will sink. If the density of the object is exactly same as the density of the liquid, it will float fully submerged. It can float anywhere inside, fully submerged. Like the submarine, which is neither rising up nor sinking, its vertical acceleration is 0 and it is fully submerged. So, the average density of this submarine is equal to the density of the surrounding water. Here we have a block of wood of relative density 0.6 floating in a liquid of relative density 0.8. Relative density is the density of the object divided by the density of water. So, we want to find what fraction of it is under the surface of the liquid. So, we start the problem by saying, let the fraction be F. Let the total volume of the object be V. So, F times V is the volume of the liquid displaced. That's the volume under the surface. That much liquid has been displaced when the object came in. So, this is the volume of the liquid displaced multiplied by the density of the liquid, 0.8 times density of water, gives me the mass of the liquid displaced multiplied by G is the buoyancy. That's the weight of the liquid displaced. Since it is floating, we have the upward buoyancy force is exactly balanced by the downward gravitational pull. So this is equal to the weight of the object. Now the weight of the object depends on its total volume multiplied by the density of the object, which is 0.6 times the density of water. That gives me the mass of the object times G gives me the weight. Now in this equation you can see that V times density of water times G is common on both sides. They cancel out. So I'm left with F is equal to 0.6 divided by 0.8, that is 3 by 4. Second problem. The object is partially submerged in water, that's the lower liquid, and partially in the upper liquid. Now the question is, what fraction is in the lower liquid? Let's call that fraction F. So, F times the total volume is in the lower liquid, and therefore in the upper liquid we have 1 minus F times the total volume. Since it is floating, the net force on it is 0, and so its weight is balanced by the buoyancy of the upper liquid and the buoyancy of the lower liquid. Let's call B1 the buoyancy of the upper liquid. That's going to be the volume of the upper liquid displaced multiplied by the density of the upper liquid, which is 0.6 times the density of water because its relative density is given as 0.6 times G, plus the buoyancy of the lower liquid. Let's write that down. The buoyancy, let's call it B2 of the lower liquid, is the volume of the lower liquid that's been displaced multiplied by density of water because that is water. That gives me the mass of the liquid displaced multiplied by G gives me the weight of the liquid displaced. Plus F times V, density of water, times G, and that's got to equal the total weight of the object. Now the weight of the object is the total volume multiplied by the density of the object, which is 0.8 times the density of water. Since the relative density is given as 0.8, that's the mass of the object multiplied by G gives me the weight of the object. So V density of water G, V density of water G, V density of water G cancels. and I'm left with 0.6 times 1 minus f plus f is equal to 0.8. Solving that, we get f is equal to half. So half the solid is in the lower liquid and half the solid is in the upper liquid. Let's go to problem number 3. So here we have a cubical block 1 meter by 1 meter by 1 meter, which is floating in a lake. Now, since the lake is made up of water and the relative density of the block is 0.7, 70% of it is submerged, 30% is outside, which means of the total height of the block, 0.7 meters is underwater and 0.3 meters is outside. So when we gently push it down until it is fully submerged, the block moves down a distance of 0.3 meters. And we need to find the work done by us when we move it down slowly. What does it mean to say that we are moving it down slowly? That means we are giving it a negligible acceleration. See, to begin with, the buoyancy cancels the weight. So the net force is 0. It's floating. Now if I gently push it down, as it moves down, the buoyancy increases. So there is an upward force now of the increase in the buoyancy, which has to be countered by my downward push. Let's say I exert a force F. Again, initially the net force is 0. As we push it down, the weight does not change. Only the buoyancy increases. So the increase in the buoyancy is the net upward force, and that has to be countered by my downward force. If my downward force is exactly equal to the increase in the buoyancy delta B, then the net force will be 0. It will not accelerate down. So in order to move it down, I'll have to exert a force F that is infinitesimally more than delta B. But that infinitesimal amount can be neglected, and so we can say that the force that I am exerting is equal to the increase in the buoyancy. Now let's say at some instant of time it has moved down by an amount x from its equilibrium position. Now remember, we start with its downward displacement 0 from equilibrium and keep increasing the downward displacement until it is equal to 0.3. So x, the downward displacement from equilibrium, goes from 0 to 0.3. When it is displaced by an amount x downwards, the increase in the buoyancy is the cross-section area times x, that is the extra volume of water displaced, multiplied by the density of water, multiplied by g, which I'll take as 10. And remember, the cross-section area is 1 square meter, so this simply becomes 10 power 4 x. So, starting with 0 force, slowly x increases from 0 to 0.3 meters, and so the force I have to exert to move it down gently is steadily increasing. Now the formula that you are familiar with for work done, F dot D, applies only to a constant force. When you have a force that is changing, see, as x increases, the force is increasing, you have to integrate. So you have to use work done is equal to integral F dot dl, which in this one-dimensional case simply becomes f dx, from x going from 0 to 0.3. And that is equal to 10 power 4 comes outside the integral, x dx, 0 to 0.3. Now the integral of x is x squared by 2. When I substitute the top limit, it becomes 0.09 by 2. When I substitute the bottom limit, it is 0. So this is 10 power 4 multiplied by 0.09 divided by 2. And the answer turns out to be 450 joules. So that is the work done in gently pushing it down. Now remember, nothing prevents you from exerting a force greater than delta B. If you exert a force greater than delta B, you give it a finite acceleration. And by the time it's fully submerged, it has a kinetic energy as well. So the work done by you will be more than 450 joules, but at the end, the block will have a kinetic energy and it will be moving downwards with a finite velocity. We don't want that. We simply want to calculate the work done in just pushing it down, which means pushing it down slowly. Well, that's it for today, folks. See you in the next video. Bye-bye.